It's a great pleasure. Hello, everyone, and to welcome everyone to the CDY seminar today. And I'm very happy to introduce Alicia Lopez-Oramas. She's at the Institute de Astrofisica de Canarias. The title of today's talk is TeV gamma ray loud binaries, and I'm really looking forward to her talk. This is a very hot topic, as we all know. So Alicia, a little bit of her background. She did her PhD at IFAE at Barcelona, Spain. She then did postdoctoral positions at a few separate places. It was CEA Saclay in France and at IAC as well. And she has also been a visiting researcher at the Institute of Cosmic Ray Research, ICRR, University of Tokyo, as well as the observatory in Rome, INFN. Alicia's research focuses on the study of variable and transient sources, mainly of galactic origin, and she has been involved in the study of RSO Fiuchi as well as gamma ray binaries. She's a member of the MAGIC collaboration as well as the CTAO consortium, the LST collaboration, and also the ASTRI mini array. And until recently, she was the science coordinator of the CTAO consortium. So welcome, Alicia, and it's really a great pleasure to have you here. And just as a reminder, our talks are usually 50 minutes, and then we have some questions, and then we just leave the floor open in case there are just some general questions. So thank you for giving us this talk, and please get started.
Well, I would like to thank you, Rashmi, Paolo, and the whole CDY team for having me today. So let me share my screen. I hope you can see the slides properly. And yeah, for me, I'm very glad to be here to be talking about this fantastic topic that are gamma loud binaries in the TeV domain, which is actually a field that has been changing quite a lot, I would say, especially in the past 10 years. We know that binaries are gamma ray emitters basically since the current generation of Cherenkov telescopes are operational, since they were identified as TeV sources very early. However, especially in the past decade and in the past few years, we have identified new types of binaries as emitters. And today, with this talk, I want to give this overview on this field. So I'll be basically talking about the binaries that are detected with the ground-based experiments, namely Cherenkov telescopes that detect gamma rays in the very high energy regime, so above 100 gigaelectron volts, more or less. You know, the current generation has Veritas, Magic. Now we have also LST1, which is the first of the large size telescopes of the future CTAO observatory that is being built in the northern hemisphere in La Palma in Spain, and there will be a southern one in Chile. And I'll also give some results on the current detectors that are located in Mexico, HAWK, and in China, LASO, that they detect the even higher counterpart, the ultra high energy emission of some of these binaries. And yeah, so just for you to know also some future observatories or detectors that are on preview are ASTRI mini array. There is the first of the telescopes is being commissioned right now here in Tenerife in the Teide Observatory. And you know, as a future detector, there will be SWIGO that will be located in the southern hemisphere. So basically today I'll be talking about gamma ray binaries that are detected with this kind of experiments. So, and which are these binaries exactly? So, binary systems, there is a very wide variety. Here I just put some of them. All of these systems are gamma loud in the sense that they emit either at high energies, very high energies, or ultra high energies. The only ones that have not been yet detected in the TeV regime are transitional millisecond pulsars, so I will not be including them in this presentation. Hence, I'll be focusing on these other 4 types of sources, which are microquasars, non-accreting pulsars, novae, and colliding wind binaries. So they emit the very high energy emission, or the TeV emission, via different mechanisms. In the case of having non-accreting pulsars, you have a massive star which provides the photon field, and then you have the pulsar wind, and it's you have these two winds that collide, and it's in this shock where you have the gamma rays produced. You can also have microquasars, in which you have a star that whose material is being accreted onto the compact object. There is an accretion disk that is created, and then you can have jets that can be created eventually, or in some systems you can even have persistent jets. Then we'll cover the topic of novae, in which you have a star whose material is being accreted into a white dwarf. And once the temperature reaches a value for burning, you have this thermonuclear runaway, and then you have these novae eruptions, these sudden increases in the magnitude. And then you have this, these are one of the most recent cases of binaries that have been discovered together with the microquasars, okay, in this regime. And then we have the topic of the case of colliding with binaries. We'll see that up to now we have only one system. In this case, you have two very massive stars with high mass loss rate, with very strong and fast winds, and you have these two stellar winds, and then you have this also this shock where you can have the gamma ray emission produced. So why did I say before that the field has changed pretty much? Because traditionally, 20 years ago, we started to have what we call gamma ray, what we identify as gamma ray binaries. Actually, the first gamma ray binary that was ever discovered was the first system that is shown here, this PSR B1259, which is composed by a massive star, an O-type star, and a 48 millisecond pulsar. So the pulsar is orbiting the star in an orbit that takes a few years to complete. And actually, we knew that it was already a pulsar, because when it's far away from the star, you actually see the pulsations. This was the first system that was actually detected by Hess. And in the like 20 years, in the first decade of operation of the current experiments, we were detecting many systems that were composed by massive stars and a compact object of unknown nature. And all of these systems were emitting in the very high energy domain. And that's what we traditionally call gamma ray binaries. But lately, we have been adding new types of sources, like this colliding with Eta Carina or the nova Ares-Ophiuchi, and more recently, over the past few years, some sources that we know for sure that they are microquasars. So you see that most of these, they display, there is a wide variety of systems. You have different companion stars, different kind of compact objects. We can have pulsars, black holes, white dwarfs, depending on the system. And also the emission changes from one type to another. So let's focus a little bit on each of these types. Let's start with what we call traditionally gamma ray binaries. So when we, the people that work in binary systems, when we talk about gamma ray binaries, we basically refer to this kind of system to the left, when you have a binary system composed by a O star or a B star and a compact object, in which the peak of the non-thermal emission lies in the gamma ray domain, as opposed to, for example, a X-ray binary. As you can see on the right, that's an X-ray binary. You see that the peak of the non-thermal emission lies in the X-ray domain. So up to now, we know 10 of these systems, like that we actually can fit in the definition, in the traditional definition of gamma ray binary, which is massive star plus compact object and peak of the non-thermal emission in this TeV domain. For a long time, we have been trying to understand which is the compact object, or why do we detect so few of these systems. Some theories say that, for example, the gamma ray binaries are actually the progenitors of high mass X-ray binaries, that that's a phase that lasts quite not for a long time in the life of a binary, so that most of the X-ray binaries that are powered by a pulsar, they are born as gamma ray binaries, and then at some point, as the pulsar powers goes down, it will convert into a X-ray binary. That would explain why, for example, you have about 300 X-ray binaries in the galaxy, and you have so few known systems. So if we have a look to these gamma ray binaries, as I said, we can see that all of them are composed by these massive stars, O stars or B stars, which are stars that also have this circumstellar disk. And when we look at the kind of compact object, you see that out of more or less 10 systems, we know that for sure 3 of them are hosting a pulsar, and for the other ones, we actually don't know. However, when we examine the characteristics of these systems, we can find some similarities and also some differences. But this can also help us understand maybe which kind of compact object is hosted in these gamma ray binaries. So you see all of them are located in the galactic plane, except for one of them, LMC-P3, that is actually located in the Large Magellanic Cloud. So it's the only gamma ray binary that is extragalactic. And as I mentioned, we can distinguish between systems that they have these B stars, so these B stars with a circumstellar disk, and stars which have as a companion O stars. So some common characteristics I already mentioned, they have massive companion stars, and they also show similar spectra and similar gamma ray emission variability. The very high energy emission that we detect in gamma ray binaries is variable with the orbit. Most of them are described by power laws, their spectra. In some cases, we see some exponential cutoff. And all of the gamma ray binaries, they have a non-thermal radio emission, but the X-ray emission is quite moderate. They are not very bright in X-rays. And what we see is that the high energy and the very high energy emission does not necessarily have to be correlated. There are some cases in which there is a clear correlation, but in some others, like in the case of LS1 or HES06, etc., we see that that actually there could be two populations of electrons that produce one the high energy and another one the very high energy component. So of course we always wonder what is the nature of the compact object, and of course if you detect pulsations or if you detect jets, you know in which case you are. But generally for these systems, we do not see pulsations and we do not generally see jets. That's why it has been so difficult to classify these gamma ray binaries. However, we see, looking again at the table, we see that some of them we already have identified with a pulsar, and we know that all of them, the emission can be described with a leptonic scenario. So by comparing the emission of all of the known systems, we could probably say that most of the gamma ray binaries are likely non-accreting pulsars. Okay. So let's go very fast through the systems that we know. So as I mentioned, the first binary that was ever discovered at gamma rays was PSR B1259. So it was discovered by HES, and it has this very long orbit. And the very high energy emission actually happens when you have the pulsar that is getting close to the star, so during the periastron passage. And recently there was just a publication by HES on the last periastron passage that happened in 2021. You can see on the left the plot. So the top is the Fermi emission, and on the bottom you can see some HES TV emission, and in blue and in green you can see the X-ray emission. And actually, what Hess found is that the emission can be described with a multiple emission zone. They saw that there are some correlations in some parts of the orbit between the TeV and the X-ray emission. There are parts in which you have X-ray emission that there is no TeV emission, which is probably the times in which you have the disk crossing. And then what they found out is also that there is no correlation with the GV emission that Fermi sees. That's what it's supporting, this multiple emission zone. And then another interesting object, which has also this long period, is the PSR 2032. In this case, we have a system in a 50-year orbit. And we actually, MAGIC and Veritas, we discovered the very high energy emission also during the periastron passage. So on top, you see the X-ray emission, and on the bottom, you see the very high energy emission. And you see that as we get closer to the periastron, the emission increase. Of course, the next passage would be in 50 years. So I don't know if we will be able even to detect it with the CTAO. So we need to maybe start thinking on the next experiment to detect this passage. So if we now go to systems with a shorter orbital period, one of the most famous traditionally also is Hess 0632. This is one of the less bright gamma ray binaries that we have. It was discovered by Hess also in 2007. It's composed by a B star, but we don't know exactly the compact object. And in many cases, we have proposed also the pulsar scenario, but of course, some authors propose that it could be actually a different kind. So what you see here on the left is the light curve in terms of the orbital phase in a paper that we did, that we accumulated like 15 years of data with MAGIC, Hess, and Veritas, and we obtained for the first time the orbital period at TeVs, that is like 317 days. And you can see here how we nicely covered the whole orbit, and we see this double peak structure. And the interesting thing of this system is that the orbital solution is still not clear. You see here on the plot 2 examples, the solution by Casares and the solution by Moritani. And you see that depending on which solution you take, the 2 peaks happen at very different places of the orbit, either at the apastron or the periastron, etc. And there are many other orbital solutions. So I really encourage people working on this. It would be really interesting to get the right parameters for this system, because it's a system that that we are very interested at, and it's still a big unknown on this regard. Then LS1 plus 61303, this one was discovered by MAGIC. It's also a B star with a circumstellar disk. And one of the most recent results that was actually quite amazing was that the FAST radio telescope identified pulsations in the system. It's a 0.27 second pulsar. So it's actually quite compatible with it being a magnetar. The interesting thing that FAST saw is that it's not periodic. So they detected these pulsations, but in the apastron, which is where we see the very high energy signal every orbit, but it's not periodic signal, okay? The cool thing of this system is also that apart from the orbital solution of 26 days, there is a super orbital modulation of the TeV emission that lasts has a period of about 4.5 years, as you can see on the bottom left. And for this, for example, we have tried, there are some models on how you can explain the superorbital emission by changes, as you can see on the bottom right, that could be explained by changes in the size of the decretion disk of the star. So, for example, in the cases in which you have a small disk, you will have your pulsar far from the star, away from the disk, and there in the apastron you will have the TeV emission. But in moments in which you have a larger disk, your emission, your TV emission will be decreased, okay? And also some nice results by LASSO is that they have detected this binary up to 100 tera electron volts. You see there on the right, on the top, that they measure power law without cutoff, and actually they also see some orbital modulation. So LS1 plus ST1303 is a binary that we have known for almost 2 decades, and it's still surprising us. And then the last of the, the first of the O-type binaries is this LS5039. It's a O star in a very close orbit with a compact object of and of 4 days. I put here, sorry, there is a typo. It's not 3.9 hours, it's 3.9 days. And you can see here that actually you have the inferior and the superior conjunction nicely measured by Hess, and also even by Veritas from the northern hemisphere. And also, HOT has reported flux modulations, and LASSO has recently reported that they see it above several tera electron volts. Then there are other O-type binaries which were actually discovered through blind searches. The extragalactic one, LMC P3, and this other one, 1FGL 1018. And as I mentioned, they were discovered through blind searches at high energies. You can see on the left that the Hess emission, you see that it's phase lock to the orbital period of the system, and you can see that there is actually a variability. But the thing is that the orbital parameters in this system are not well constrained neither, and that we don't know what the compact object is. And in the case of 1FGL, you can actually see that the Hess flux in red is also variable, and in this case, it's correlated with the Fermi and the X-ray emission, which is not the case as in the other one, as we can see on the left plot. And then one of the most recent discoveries is the type of companion that is in Hess 1832. This is a source that was already reported 10 years ago by Hess, and a few years ago there was some periodic modulation found in the Fermilab data, so it was identified as a new gamma ray binary. There is no optical counterpart, but it's coincident with an infrared source. And then it was identified that the companion is a O6 star. And the interesting thing about this paper that was published last year is that they talk about the apparent grouping that is happening in gamma ray binaries, that all the O-type gamma ray binaries have spectral types of type 5, O5 or O6. And the authors think that it's connected to the connection between the initial mass function and the wind momentum luminosity relation. So in principle, we know that the initial mass function tells you that the number of stars decreases with mass. So spectral types that are earlier before O5 are rare. And due to the connection between the wind momentum luminosity and so, that's why all of these O-type stars are being grouped in types O5, O6. And then if you need, or if you have a binary that has a later spectral type, they will form with the B stars because they have this denser wind due to this circumstellar disk. So how many more binaries can we expect? So there are some. I took this slide from Guillaume Dubus, and if you do some population studies, and so you can you can estimate that you will have actually a population that is at least 10 times larger than what we have now. And we can expect to have about 140 systems. So for sure, future facilities such as CTAO will be key in identifying new gamma ray binaries. And so just to summarize a little bit everything that I said about gamma ray binaries, so what we traditionally call a gamma ray binary is a binary system in which you have a massive star with a compact object that is not likely a non-accreting pulsar. And in the case of O-type systems, they are grouping apparently in this O5, O6 type. And now we know that they can even emit up to ultra high energies, and that we can really expect a larger population, at least 10 times of what we have now. So moving to recently added types of binaries. So a few years ago, we detected the first nova in the very high energy regime. Is this system that you see here, Ares Ophiuchi, is composed by this red giant star whose material is being accreted into this white dwarf. We already knew that the novae were sources of high energy gamma rays for a long time, because Fermilab already identified both symbiotic, which are when you have this red giant star, and classical, which is when you have a main sequence star. And actually, Fermilab already had detected both symbiotic and classical novae and had identified with the high energy sources. However, you see here that the SEDs were actually measured always up to maximum 10 gigaelectron volts. Novice, there are many optical novice. The discovery rate in the galaxy is about 5 to 15 per year, because even if the eruption rate in the galaxy is much more, the calculated one is much more. And with Fermilab, we know that we get like one high energy nova per year. And so the question was whether they also emit at very high energies. And as I said, a few years ago in 2021, in August, this recurrent system, Ares Ophiuchi, entered its outburst. It happens every 15 years. And in 2021, we detected it for the first time. So Ares Ophiuchi is the first and the only nova that we have observed in the TeV regime. You see here on the left the Hess plus Fermilab light curves, and on the right the magic Fermi and optical light curves. And this helps settling novae as a new types of very high energy gamma ray emitter. And the question is that whether we can fit a leptonic or hadronic scenario. And what we see is that actually the gamma ray emission is best fit by a hadronic scenario. Hence, we have protons being accelerated in the nova ejecta. And we see that generally, if you study the evolution from the first day to few days later, you see that there is a hardening in the spectra, which is in line with the expectations from the cooling and acceleration timescales, and it tells you that you have protons being accelerated. And when you compare Ares Ophiuchi to other novae, it doesn't have any big peculiarity. It's just that it was actually the one with the highest flux and the brightest one, and that's basically why we detected it, no? And now we know that the novae, they are proton accelerators. So we calculated how much they contribute to the overall galactic cosmic ray flux. And what we saw is actually that it's a very little contribution to the overall emission, but that they can indeed increase the local density, creating bubbles that in the case of recurrent systems can have a size of about even 10 parsec scales. And well, in total there are about 10 non-recurrent novae in the galaxy. Those are the systems with the recurrent timescales. And one of the most famous right now is T Corona Borealis. I will show you in the next slide. And one of the open questions is like, can classical novae be also very high energy emitters? They were surprisingly high energy emitters. So the question is, can they emit at TeV energies? The problem here is that you don't have this dense medium in the case of symbiotic novae, but there are some authors that say that actually you can expect emission in the TeV domain. So hopefully we'll have some classical novae observations soon, and we will understand if they can be TeV emitters or not. And so T Corona Borealis, a very famous system. You have this red giant with this very massive white dwarf, and it's a recurrent system. It has a period of about 80 years. You see on the right the light curves of the last eruption, and it's actually very bright. The peak of the outburst is about magnitude 2.9. Okay. And it's 3 times closer than Ares of Yuki, so you can really expect a very, very bright, very high energy signal. And so the system it's always bright. It's you can see here the B and V magnitudes, and before the peak there is this pre-eruption dip in which you can see that the system already entered in 2023. So the expected eruption date was April last year. It still haven't erupted, so we're a little bit late in that sense. But yesterday there was an ATEL that from this group in which they saw some increases in the accretion rate, but not in luminosity. Okay, so if you look at the light curve on the right, the magnitude is quite stable, but you can see here on the H alpha and the helium-2 lines how they have really changed shape in the past days, okay, or in the past few weeks. So this means that that the accretion rate is increasing, and that eventually we will get finally this nova eruption. So we should really keep an eye on it. And then colliding WIM binaries is another of the types that were identified as a very high energy emitters. So in this case, we have 2 very massive stars, and it's in this colliding region between the 2 stellar winds, in which you can have eventually in which you can have the gamma ray emission. So up to now, the only colliding wind binary that has been found to emit gamma rays in the TeV domain is Eta Carina. So you have these 2 supermassive stars. Eta Carina, there is a 100 luminous blue variable star, and this Eta Carina B, that is an 30 solar mass star, and they are orbiting in a very eccentric orbit with a period of about 5.5 years. And so you have this high mass loss rate, these supersonic winds, and has detected emission during the periastron passage already 10 years ago. And they just recently, like a few weeks ago, they published, or the paper was put in archive, where they studied the 2020 passage. And actually, you can see here that now in the SCD, they can actually fit their SCD with a hadronic scenario, and you can actually also see what the light curve looks in the both with Fermi in blue and with Hess in red, and you can see actually how the emission, when there is some detection where you have the periastron. Okay, so the next passage is actually this year, so I guess we'll have much more interesting news from Hess on this topic, hopefully soon. And then microquasars, well, you know, this is also one of the real hot topics in the past few months. And actually, in this seminar series, there were a lot of sessions already dedicated on microquasars by the people actually really discovering this emission. So I'll be very fast. Because if you want to really learn more, I advise that you check the YouTube of the recordings of these talks and enjoy. So in the Cherenkov community, we have been searching for transient emission from microquasars for decades. No, you know that they go these periods of activity, and actually that's what we have been always trying to do, and what we still try to do. We have observed high mass and low mass systems without success. The strongest hint of emission that we had is that of MAGIC in 2006 of Cygnus X1, a 4.1 post trial. And since then, we haven't seen any other microquasar strong hint, let's say, okay? And the surprise came a few years ago when Hawks reported the detection of very high energy emission from the interaction regions in SS453. This was later confirmed by Hess after 200 hours of observations, and you can see how this emission is coincident with the X-ray shocks. And just you know that there is also this Fermi-Lat emission that is not actually in align with the jets that I also put there for comparison. So this was the first surprise. It was the first microquasar identified. You see that there is jet medium interaction. It has a leptonic origin, as reported by them. It was also recently confirmed by LASO, and even Veritas in a conference recently. They also show some results. Then LASO also reported that they have some emission at the 100 TeV, that it's coming from the central region, and that it has a hadronic origin. So the LASO actually claims that the black hole jet systems can be factories of cosmic rays around the knee. So a lot of news regarding this system. And not only that, since then, we have had many more microquasars being reported. The second one was 4641. Again, Hawk discovered some emission, confirmed by Hess, confirmed by LASO. And actually, 4644 is even brighter than SS453, and it's what they call a super pevatron, where you have protons up to 10 PeV, because the highest energies photons are almost 1 PeV. And and in this LASO paper, they identify also other systems, Yares 1915, MAXI J 1820, and Cygnus X1 that they report at 4 sigma level. So what have we seen of this system? So for example, in the case of MAXI 1820, there was a campaign of MAGIC, Hess, and Veritas in 2018 when the source was discovered when it was in outbursts, during outbursts. And actually we observed for 60 hours above 200 giga-electron-volts. But as you can see here in the combined values, there was no emission reported. However, if you look at the numbers, it was probably below the sensitivity, right? Because if we have a look to the Hess detection on SS433 and for V4641, and comparing to the fluxes that LASO see for each of these sources, we would potentially need to have observed this one for much more time, in the order of hundreds of hours, no? And regarding Cygnus X1, I already mentioned that there was this transient hint many years ago by MAGIC. And for example, MAGIC already observed 100 hours of Cygnus X1 in the past, mainly during this hard state, so when the jet is active, and still we didn't get any signal. Potentially, we need to keep observing for many more hours to be able to detect it, especially because if we have a look again to the LASO claim, you see that still it's at 4 sigma level, so the flux is quite low compared to these other microquasars. But still, we are hopeful we can still detect maybe transient emission from microquasars. We made some calculations with what we can expect with CTAO, and potentially we will be able to detect transient signal from the Cygnus X1, Cygnus X3, and even maybe for some low mass X-ray binaries in which the jet and the jet is more or less pointing toward us or doesn't have a very large viewing angle. And so just to finish, so I reported here or tried to summarize the 4 types of gamma ray binaries or binaries that emit at very high energy gamma rays. We know that what we traditionally call gamma ray binaries have a leptonic origin of the emission inverse Compton novae. For the moment, they are best described by hadronic scenario. Same for colliding wind binaries. In the only one that we know recently, we learned that it's best described by a hadronic. And then in the case of microquasars, we see that the emission is mainly leptonic. And then in the case of SS433, the central source, there seems to be some hadronic component. Well, and in many of these sources, I mean, for example, there is also this hadronic component. Okay, so depending on the region that you analyze and the energy, you have these two components. Okay, so these are the conclusions. I'll leave them here, but I just want to finish saying that there are still many open questions, because especially in the case of novae and colliding wind binaries, we only have one system of each. So there are many things that we still need to learn. And still, as I mentioned, what is the compact object in gamma ray binaries, or can we detect transient emission from microquasars? When is the corona borealis exploding? And many other questions. So that's all from my side. So thank you.
Thank you, Alicia. That was really great. Thank you very much for the great summary. Let me just see if there are any questions. Maybe I can start with a quick question, and then we'll take from others. So you mentioned the Maxi J. Can you go back to that slide?
Yeah. This one.
So I remember there was an outburst, and there was the IACTs had a follow-up.
Exactly.
And spent some time on it. It was combined, I think it was 60 hours, and there was but you think we stopped too early, or it was just not bright enough, or
actually, I think that's a good question, no? Because if you see at the LASSO, so I think in general we need to accumulate much more time, no, to detect the microquasars. No, we are seeing that in the order between 100, 150, 150
yeah.
hours. Also, if you see at the LASSO emission, so Maxi, it entered in outburst in 2018, and the LASSO detection was around 2021. No, I think they accumulated data between 2020, 2021. I don't know if in 2022, I might be wrong, but if someone remembers, please correct me. But actually, the fact that they detect this emission might potentially means that these radio jets, or that the jets are active for a longer time than what we expected in the beginning, no? So I don't know if the question is that we really just needed to integrate more time, or maybe we also needed to wait a little bit of time. I don't know if it's protons, if they need a longer time to accelerate and to produce a very high energy emission. So yeah.
Okay, great. Thank you. Yeah. So questions, Susumu, please go ahead.
Yeah. Hi, Alicia. So for the famous gamma ray binaries, LS5039 and LSI, forgot the exact number, but anyway, I remember when they were first discovered at VHE, they were actually touted as microquasars, and I believe they do have some extended radio emission. I remember later on, it was some people showed that maybe the extension of the radio emission might have some correlation with the orbital phase, which might indicate like a pulsar wind origin. What is the latest situation with the radio morphology? Latest understanding?
Yeah, I actually don't know. I haven't seen any recent radio publication regarding these two binaries. So if someone else in the audience knows, that would be great. I mean, I just know that as I mentioned here, that the FAS reported these pulsations, but I don't know about any radio structure in the system. And yeah, and in LS5039, I neither have any news on radio.
Yeah, okay, thanks.
Yeah.
Valenti maybe wants to comment. Go ahead, please.
Yeah, thank you. Thank you, Alicia, for the talk. I have a comment about this radio thing, and then a comment about Maxi 1820 and LASO results. So regarding the radio, there are these papers which have been published over the years about the analysis, reanalysis of the observations published by the one and collaborators in 2006, done by the group of Maria Massi. And I think they also did new observations, I'm not sure. But basically, they were showing that on BLBI scales, like tens of astronomical units, they were seeing this structure which was moving around the binary system, which could be related perhaps to a colliding wind structure, like a shock wind structure. As the orbit was going on, the structure was moving around. But the group by Massi, they were proposing that it was related to a precessing jet, which I'm dubious about. But in any case, that's basically the state of the thing since already quite like several years. For several years, it has been like that. In the case of LS539, if I remember correctly, the most recent paper showing the BLBI radio structure is the one by Moldon et al. In 2012, and they basically showed something relatively similar to what was seen in LS161303, let's say, with a lot of caveats, but relatively similar. Now we had all these simulations done for wind-wind interactions, and in high mass microquasars, in both cases, you expect these kind of structures to appear, like some kind of structure precessing around or rotating around the orbit due to the interaction with the massive stellar wind. So either you have, in both cases, you have a jet or you have a pulsar wind, you could have this kind of radio images. Although maybe with a jet, it's a bit more complicated to get such a level of how to say. Well, it's like a very clearly rotating structure, and for a jet, you need something which is very much impacted by the stellar wind if you want to get something like that. That's regarding the radio thing. I'm sorry, I spoke a lot.
Thanks, Valenti.
Thanks. Helpful.
Yeah, you wanted to ask or comment something, no, on the LASO sources?
Maxi, yes, exactly. So I was checking in the paper, and I think I had talked with Royo about this. I'm not sure if it was Royo, but well, there was this question about where is the center of gravity of the Maxi source, because the source, if I remember correctly, it appears like point-like for LASO, but the center of gravity is shifted by a few sigma, taking into account the error of the center of gravity from the binary. So even if the structure is compatible with a point-like source for LASO, it seems to be located at some distance from the binary, which would indicate that it's to some level, to some extent, it's extended. So if it were extended, then we have a very large source of maybe at 0.1 degrees, something like that, which would mean that you need a lot of time to accumulate particles to produce the observed emission.
Okay. Thanks, Valentin.
Can I quickly ask a follow-up maybe to Valenti? So for MAXI J1820, is there radio observations? I mean, did you just mention that there were some, and have people seen jets or anything? No, not for MAXI J.
For MAXI 1820, I don't know what is the situation in radio. I don't know. I think that there were these outbursts, but
I think superluminal motion was clearly seen.
Yes, this is the original. Yeah.
Yeah. So I think a jet was well, in the radio, it was followed out to something like parsec scales, if I remember correctly. I'll immediately check the reference and try to come up with it. Yeah. So yeah, there was a jet seen, but only on small scales. I mean, compared to like what we see in SS433 or V46.
Okay, thank you. Questions? Any other questions?
Maybe one for you first. Sumo, are the radio jets aligned with like the lasso or the TV structure? Like in V4641, it wasn't clear if that was the case.
So in the
yeah, go ahead.
Yeah, sorry, go ahead either.
Yeah, no. Well, so in the case of 4641, there was this there is this radio image that it's already quite some years ago, in which you have like something that it's a radio image that compared to the size of these huge things is actually really small. Okay, it's like a more binary scale. And this is what an image that was used to say that is supposedly a microblazer in which you have the jets pointing towards us. Since then, I haven't heard of any other detection or any other large scale radio structure. Maybe Susumu, that is in contact with radio people, maybe he knows better. But yeah.
No, I don't know. Yeah, as far as I know, there's certainly this doesn't seem to be obvious radio counterparts. There was a recent paper for X-rays with the extend CCD on CRISM, not the calorimeter, where they seem to find a bit of extended emission, but the field of view is not large enough to cover the entire structure seen in gamma ray, so it's not clear how that might be correlated.
If I remember correctly, I think that if you check Laura's presentation of some months ago in this same series, I think she had some plot on the radio and on the gamma emission, and that was very nice to see the scales. So I recommend people to go check her talk.
Thanks. Yeah.
Any other questions? Valenti, do you have another question? Please go ahead.
Yeah, well, thank you. It's a sort of comment if other people are not raising their hands. I was thinking about B4641, and I think that the size of the structures this slide shows, it's roughly similar to the size of the structure in SS433. But at the same time, the power in SS433, it's very, very large. I personally don't think that V4641, it's conspicuous sometimes in its activity, but it's not by far something as conspicuous as in different wavelengths as SS433. So I would say that energetically it's less powerful. So in order to see something in radio on 100 parsec scales, probably you need a power to fill with non-thermal electrons the bubble, which is significantly higher than the one in 4641, which basically implies that you wouldn't see much in radio unless you manage to have a very, very deep observation on those scales, because there are not enough radio electrons to produce even also magnetic field to produce detectable radio, even if the source can be seen relatively easily in gamma rays on those scales.
Thank you, Valenti. Any other questions?
Maybe I had one, or in the audience, I noticed that Robin Corbett here was a kind of expert in X-ray morphology of binaries. Do you have any comments overall comparison of TV with gamma rays and X-rays and radio?
I'm not sure that the morphology is necessarily my speciality. More the timing and trying to find the new ones that way, I would say, is the emphasis of my stuff. So I think you're probably as up to date as I am.
Okay, thanks.
Well, maybe I can ask one last question and we can then maybe wrap up. So you mentioned something about the O-star companion, and it's a particular spectral type. Is that I think I may be out of touch and I may have missed that.
Yeah, actually,
Is that pretty consistent now that that's what it seems like? It's a spectral type 056 for these
so if you check all of the O-type gamma ray binaries, so LS5039 is a 06, then you have 05, 06, this one is 06 too. And yeah, and so if you check this paper that was published last year, it seems that indeed there is this grouping, no? I mean, it's at least apparently it's there, no? On this 05 or 06. And well, I didn't put the plot here, but the authors comment on why you can potentially have this group.
That's really interesting. Okay, I'll look into it.
Check it.
Okay, Matthew Lundy, you have a question?
Yeah, thank you for the talk. I had a question actually about the colliding wind binaries, and I'm wondering about kind of the prospects for progress on those sources, because although we only have one, I think we only have one for a very good reason, which is that it's tremendously brighter than all the other ones. And so I was wondering if you saw any prospects for making progress on purely wind-driven massive star systems.
Yeah, that's a great question, because actually Eta Carina is quite unique, no? And all of the other colliding wind binaries, you have less massive stars, and I think it's tricky, at least with current generation of ICTs, it's tricky because at least in the northern hemisphere, you don't have too many good candidates. Maybe there are like 2 or 3, I would say. And as I mentioned, they are less luminous, so they have this the mass loss rate and the wind velocity. They are less there. So I think it's tricky. There are some good candidates in the sense that, for example, WR140, you have this X-ray radio emission in many of the systems. You know that there is non-thermal emission, but yeah. I think potentially there would be like maybe good candidates for CTAO. For right now, I think it's going to be tricky to detect more systems. Yeah, it's a good question.
Thank you.
Thank you. So there were some comments in the chat. People can take a look at some. Susuma, thank you for posting the talk. Sorry, the paper. And maybe I'll just ask if there are any last questions. If not, let's thank Alicia again. And let me just remind people that in 2 weeks, we have a talk by Phil Carrot on results from IXPE with a focus on gamma ray binaries. So please join, and yeah, see you again. Thank you.
Thanks, Alicia. Thanks.
Bye.
Bye.
Thank you.
Thank you. Bye.
Bye-bye.